Alright, before this video, I just want to give a quick shout out to my kids at school who were good sport about just suiting up just because we want to. Diego, Hung, Aaron, Vincent, Tyler, Kyson, Caden, Carson, Adam, Ethan, Brian, Apollo, Lamb, Sam, that is Alvin, Eric Ty, Ethan, that's Dat, that's Jack, that's William, that's Kyle, that's Aaron, that's Harrison, that's Caden, that's Nathan in the back, that's Hunter, William, Rayanne, Derek, Elton, David, William, uh, Hugh, excuse me, and then this is Anthony, Vong, and Emily. All right, let's do this one. So here we have a ball of mass m1 kilogram. It's thrown from the top of a building at an angle of 47 degrees to the horizontal with an initial speed of 13 meters per second. It says the ball is thrown at a height of 58 meters above the ground, and it hits the ground 40.294 meters from the base of the building. All right. So here's A, B, C, D, and E. If you need to pause it, read for yourself. Otherwise, I will just get cracking. Let's do part A. What is the kinetic energy at the peak of the flight? So to find the kinetic energy at the peak of the flight, keep in mind that in projectile motion, at the peak of the flight, the velocity in the y component or in the vertical direction approaches zero because it has to come back down. So in my diagram here, I put Vy at the peak as zero. However, there is a horizontal component still because the object is moving rightward. So y goes to zero, but Vx stays constant. Okay, so here's Vx. So therefore, to find the kinetic energy at the peak, all I need is Vx. So here I have generically Ke is equal to 1/2 mv squared, but V here being Vx because it is the only velocity component that exists at the peak of the flight. So here in the diagram, you're given the initial speed is 13 meters per second. Its angle at 47 degrees. So here I can find Vix real quick. To find Vix, which is the same as Vx, which is the same as Vfx because Vx is constant. Vx here is just V cosine theta. It's cosine because it is touching the angle, and this is the adjacent leg. All right, so V being 13. So if you plug in V being 13, cosine being 47, you'll get that Vx is 8.87 meters per second. And keep in mind, in projectile motion, Ax is 0, so Vx stays constant throughout the whole entire flight as it leaves the person's hand and goes all the way to the ground, or at least right before it touches the ground. All right. Here I have mass 1 kilogram. I'm just going to plug in Vx. So keep in mind that you want to plug in Vx, okay? A misconception is that you plug in 13. That's not the case. At the peak of the flight, the velocity is not 13. It's just 8.87 because it's Vx. All right, plug in a calculator. You should get a value of about 39.34 joules. And that is your answer for part A. Part B asks you to find the kinetic energy just before it strikes the ground. So there's different ways to do this. Here, I'm just going to set up mechanical energy equals to final mechanical energy. Hopefully the system is assumed to be, in a isolated system or conservative system here. No air drag. PE plus KE, I equals KE plus EF. Here, I can cancel out PF due to gravity because once it lands, on the ground or just right before it touches the ground, H is super, super small that, the MGH term is just pretty much zero. All right. Other than that, I'm just going to break it up. PEI equals MGHI. KI is just 1/2 MVI squared. And then KF I'm going to leave as is because part B asks you to find the kinetic energy. So I need to just keep KEF as is. I don't need to break it up. Here, everything is given. Mass is 1. G is a positive 9.8 because this is energy. So it's a scalar quantity. So we want to use a positive 9.8. Height from ground up is a positive 58 because ground being 0 and the ball is being thrown initially at a height of 58 meters in the diagram there. All right. Other than that, 1/2 from the KE term carries down. Mass is 1 and VI here, the initial velocity or the initial speed is 13. And then we're going to square that. If you do all that correctly, the first term is going to give you 568.4. And then the second term is going to give you 84.5. If we add those two values up, the kinetic energy just right before it strikes the floor is 652.9 joules. All right. Other than that, let's go now. Hold on. Before I get to part C, though, like I said, there's different ways to do this. You can apply the work kinetic energy theorem. Here we go. Delta Ke, I'm just going to break up into Kf minus Kei. So here, we have to identify what force is doing the work. The moment it leaves the person's hand, the only force acting on the ball is in the vertical direction, which is F of G. And it's going to rise and it's going to come down. While it goes across, there is no force acting on it in the x direction. So there's no work done in the x direction. There's only work done in the y direction because there's a force and there's also a displacement. So it went up and came down. Okay. So here you notice in my network function, I broke it down to force times displacement. But what force? The force due to gravity, which is pointing downward. Well, my vertical displacement here is also going to be downward because it starts at 58 and it's going to go down 58 meters before it strikes the ground. All right. Other than that, I'm just going to go ahead and isolate for KEF by moving a negative KI to the left side. Here, I'm just going to plug in things. F of G, I'm going to break it up into M times G. Delta Y I can carry down. KEI is 1/2 MVI square. And here we know everything already. M is 1. G here, it's negative 9.8. Why? Because force is a vector. So here, mass is 1. G is negative 9.8 because F of G is pointing downward. However, keep in mind that delta Y here is also negative because the object starts up here, and by the time it strikes the floor or ground, it has landed below where it started. Below would imply that it has fallen down, which imply that displacement is negative because displacement is a vector. And if you plug all the numbers in, 1/2, m being 1 here, and then the speed, the initial speed, which is thrown as 13, you square that. So the the sum of this whole entire term on the left side will give you the same answer. Okay, so it's 652.9. As you can see, the answer comes out the same regardless of which methodologies you apply. All right, let's go ahead and crack out part C. Part C asks you to find the speed of the ball just before it strikes the ground. Well, here I already have KE in part B. KE previously found in part B, so you need to rewind the video, which is 652.9 joules. Well, it asks for VF. So here I'm just going to plug in mass being 1, VF square is my unknown. And then I'm just going to multiply both sides by 2. So I need to get rid of this 2 in the denominator. So I'm going to move it to the top left numerator. So 652.9 times 2 is 1305.8. And then 1 kilogram here makes things a little nicer. All right, other than that, you have VF square. To get VF, square root both sides. And then if you square root both sides, you get VF. And then the square root of 1305.8 will give you 36.14. Okay, so that is the speed. It's not velocity, that's just the magnitude of your velocity because your velocity has a direction, but here it asks for speed, so I'm done there. However, if you wanted to, you can use old school kinematics if you like. Here's my VF, or here's the vector, here's the velocity vector, right? But part C only asks for speed, so all I have to do is find just the length of this hypotenuse. So keep in mind that earlier I stated Vx doesn't change, so Vfx is the same as Vix, which is the same as Vx. So once you find Vix, it stays the same throughout the whole entire problem. Okay, so I know Vfx is already 8.87. What I don't know is Vfy. Okay, so to solve this right triangle, I need 2 legs, or I need 2 legs and an angle. But here, I have this leg already, Vfx. The only thing that I'm missing really is Vfy, but I can use kinematics to find that. So once I do that, I can just use Pythagorean theorem. All right, so here we go. I'm just going to do Pythagorean theorem, Vf square, which is this hypotenuse, right, equals Vfx square, which is this leg here, and then Vfy square, which is this vertical leg. So once again, you have a right triangle. So I'm just going to plug and check. Vfx, I know from my starting point, is 8.87. I want to square that. What I don't know is my Vfy, right? I need Vfy so I can square it. Well, I can use kinematics. When you use kinematics, make sure you're consistent with directions here. Here, I'm just going to focus my attention in the y direction because I need to find Vfy. So subscripts is super important here. So Vfy squared equals Viy squared plus 2g delta y. Here, in the diagram, it didn't give you what Viy is, but I can find it. It's the same methodology as finding Vix. If Vix is V cosine theta, therefore Viy is just Vi sine theta. So if you punch Vi being 13, sine of 47, that will give you 9.51. So I know Viy is. So Viy is going to be 9.51. I want to square that. G here being the acceleration due to gravity, which is negative 9.8. My delta y is my vertical displacement, so it's negative 58 because once again it's fallen downward from the starting point. Okay, so if you plug all this stuff in, the negative times the negative makes it a positive. So 9.51 squared is going to give you 90.44, and then 2 times 9.8 times 58. Or again, you can say negative and negative if you want, but 2 negative signs will make a positive. That'll give you 1,136.8. If you sum up the right side, that'll give you 1227.24. But once again, this is Vf squared, which I'm actually going to keep as Vf squared. Okay, why? Because I don't want to square root it and then square it again. So you notice here where my cursor is circling, I need Vfy squared. I actually have Vfy squared. So I won't square root it here. I'm actually just going to use this value of 1227.24. All right. Other than that, I'm just going to carry the statement down. So VF squared is equal to 8.87 square. And then the whole term, VFY square itself, is equal to 1227.24. And if you square 8.87 and then add it to the 1227.24, you'll get 1305.9. But then don't forget, we're trying to get VF. So therefore, to get VF, square root both sides. And if you square root 1305.9, you'll get 36.14, which is the same as doing just the kinetic energy. I would use the left side because it's hella quicker. Okay. All right. Other than that, let's go ahead and crack out part D and E. Part D asks you to find the net work done on the ball from the initial position to the peak of the trajectory. So here, net work is equal to delta KE. I'm going to break delta K once again into KEF minus KEI. And then here, I'm just going to expand KF to 1/2 MVF square minus 1/2 MVI square. Here, mass being 1, but you notice here it says to the peak, right? To the peak. So here's the ball, it got shot or thrown, whatever, and here's the peak. At the peak, my final velocity is only Vx, which is 8.87. And that's why Vf here is 8.87, because Vf now references the peak of the trajectory. All right, other than that, Vi is 13 because you're throwing it at an initial speed of 13. So if you do that correctly, you'll get the first term is 39.34, and then you're going to subtract it from the initial kinetic energy, which is 84.5. And then if you do that, you get a work of negative 45.16 joules. Work is negative here because as you are traveling upward, your delta Y is positive, but F of G is pointing downward. So therefore, a negative times a positive makes a negative. So we say this is work done by gravity against the object's motion. So the object is trying to move upward, but gravity is pulling it down. All right. So therefore, the answer for this one, the net work on the system here, is negative 45.16 joules. All right. If you don't like that, you can also do this. All right. You can say that net work is equal to force times displacement. As I stated, what force acts on the object? Just F of G, because there is no Fx, because Ax is 0, because Vx stays constant. Other than that, identify what F of G is. F of G is simply mass times gravity, and then delta Y is, again, as the object is moving up and down, so that is the only work done on the ball at this moment. Here, mass is 1, G being negative 9.8, and then delta Y here is my unknown. But I can find delta Y really quick. I don't know how high it went before it came to a stop in the vertical direction and then falls back down, right? So therefore, I can just use common form, or this kinematics equation, Vfy square minus Viy square equals 2g delta y. Here, Vfy is going to cross out because at the peak, the V in the vertical direction goes to 0, as I have here in the diagram. Vy at the peak is 0. So I'm going to cross that term out. Earlier, I already found VIY. VIY, once again, in case you didn't follow along, VIY is simply VI times sine of 47, which will give me 9.51. So here, once again, I have VIY already. I know G, so the only thing I'm missing here is delta Y. So I'm going to plug in. I'm going to carry the negative sign down. So the negative sign in front of VIY squared, I'm going to carry that down. VIY itself is a positive 9.51. I'm going to parentheses that. I'm going to square that. And then here, G being negative 9.8, because this is a kinematics equation. And if you do that correctly, it tells you that the ball rises a vertical displacement of 4.61 meters before it falls back down, or it turns around in the Y direction. All right. Other than that, I know delta Y. I'm just going to plug it in. So I'm just going to say work is 1 kilogram times negative 9.8 meters per second square. I was missing delta Y, but now I found that delta Y is a positive 4.61 because it's on its way up. So therefore, I'm just going to plug that in. So as you can see here, you have a negative sign here in this product. 1 times negative 9.8 times 4.61 will give you a value of negative 45.18 joules. I know the rounding odds off a little bit here. However, as you can see, big picture, the answer is negative because it's work done against the object's motion. Therefore, the work here is negative, and the value comes out pretty much the same. All right, on that, let's crack out part E. Part E asks you to calculate the time of flight for the whole entire motion. So here, I think the easiest way for me to do it is just delta Y is equal to VIYT plus 1/2 GT squared. You notice here I wrote VIY, not VI, so it's important as you do motions in 2D, make sure you keep your V's with subscripts. Okay, so here's delta Y. I'm purely looking at the Y direction because it dictates the time of flight. So I need to use VIY, not VI. So be consistent. And then here, acceleration is acceleration due to gravity because the gravity is in the Y direction. So I'm just going to plug in values I know. For the whole entire motion, I'm just going to look from start to finish. From start to finish, the ball falls a vertical displacement of negative 58. It's negative because it fell down. VIY, I found earlier, this is VIY is pointing up, so that's a positive 9.51. T, I don't know because that's what I'm trying to find. And then 1/2, G being negative 9.8, because once again, these are kinematics equations. The acceleration due to gravity is pointing downward. Here's T squared, so I'm just going to simplify this real quick. All right, 1/2 times negative 9.8 is negative 4.9. I want to put that term first because it has a T square. And then I'm just going to, what I'm doing is I'm just rearranging it so it looks like a quadratic. Here, 9.51t is the second term because this is t. And then this negative 58, I want to move it to the right side, which makes it positive. Setting the whole function equal to 0 allows me to do quadratic. So here I can pull out my a, b, and c real quick. My a is going to be negative 4.9. My b is going to be 9.51. My c is going to be a positive 58. So I'm just going to exit the screen, punch this in my quadratic software online here, which I like to use. Okay, so here my a was negative 4.9 because it's 1/2 times 9.8. My b, which is VIY, which is 9.51. And then my c was a positive 58 because I moved the negative to the right side to set equal to 0. And when I do that, and I should get two values. So here it says t is equal to negative 2.6, which makes no sense because t can't be negative. So the answer is going to be 4.5451. Okay. All right, that's that. So let me go ahead and run this back. Okay. All right. So therefore, t for this particular problem is going to be about 4.51 seconds, and that is the easiest way I think for me to find t. If you want, you can use other strategies if you like. Okay. All right. Other than that, stay nerdy. Don't be whack.